Welcome to Chapter 5. So in this chapter we're going to be talking about nuclear radiation, nuclear chemistry. So radioactive decay is actually what happens when an unstable nuclei emits particles or releases energy in order to become stable. So there are some configurations of nuclei between the protons and the neutrons where there isn't enough kind of interference between the positive protons to keep everything together. So if you remember when we were talking about the strong nuclear force, we said that the neutrons are really there to kind of separate the positive charges enough that the strong nuclear force can work to hold the whole nuclei together. Well, in some nuclei that doesn't actually work so well. So those are called unstable nuclei. And eventually, it doesn't always have to happen very quickly, because usually we think about radioactive decay happening instantly, but it doesn't actually have to happen that quickly. It can happen over thousands of years. Okay, but eventually these unstable nuclei are going to start losing things in order to try to become stable. So this only happens in certain isotopes of some elements. So as you go further down the periodic table, you're adding in protons and neutrons, so you're more likely to have unstable isotopes. Okay. Generally, the smaller elements don't have unstable isotopes. Some of them will, like carbon-14 is an unstable isotope. Okay. But generally, the smaller the atom, the less likely it is to have a radioactive isotope, or the less likely it is to have several. Okay, because there are some of the bigger ones that have multiple different radioactive isotopes. So most elements have at least one stable isotope. Okay, so those are isotopes or atoms that are not going to try to break apart. And some of them, especially some of the larger ones, don't even have one stable isotope. So if you look at the highest number, the highest atomic numbers, most of those are synthetic and they fly apart within milliseconds, or even smaller than milliseconds. So a lot of that research is done in a split second when the atom forms. So those elements don't have a stable isotope. So after radioactive decay, the element is going to change into a different isotope of the same element, or it can actually turn into an entirely different element. It depends on what type of radiation there is and what's left over after the radiation. So nuclear radiation is the energy and matter that is released during radioactive decay. So when the nucleus of an atom starts to break apart, it releases that nuclear radiation. So it can affect materials that are bombarded as well as the material that releases the radiation. Okay, so it'll leave behind a different atom than when it started, and then anything that it hits or bounces off of, it'll affect as well. There are 4 major types of nuclear radiation that we're going to talk about. So you have your alpha particle, your beta particle, gamma rays, and neutron. All right, so starting with alpha particles. These are the biggest ones, okay? So alpha particles contain 2 protons and 2 neutrons. Oftentimes it is written as 4/2 He, okay? Because if you look at this, you've got 2 protons, 2 neutrons. That is actually the nucleus of a helium atom, okay? So that's where this symbol comes from. It does have a mass in kilograms of 6.646 times 10 to the negative 27th. Okay, so it's a really tiny mass, but again, this is the largest out of the 4 types of radiation we're going to talk about. And so it actually has the most mass. So when this goes bouncing off of things, it can actually do some damage, okay, just by its mass alone. It does also have a positive 2 charge, so that positive 2 can start interacting with things. And then alpha particles, again, are 2 protons, 2 neutrons. So a helium-4 atom which has 2 protons, 2 neutrons, without electrons, is the same as an alpha particle. So it's basically just the helium nuclei is the same as an alpha particle. It is the most massive type of nuclear radiation, so it is the largest, and it also has the most mass. And they don't travel through other materials easily, simply because of how large they are, but they can ionize any materials they interact with. So with those positive charges, it can start pulling electrons off of different things that it bounces off of, which would create a negative charge on the material that it interacts with. So next up, we have a beta particle. So this one is just an electron. Okay, so this is kind of a weird little symbol thing that happens here. It's 0 over -1 e. So the e is talking about the electron. Okay, so it has an even smaller mass. So if you remember, the alpha particle was times 10 to the -27th. Here we have 10 to the -31. So this has negligible mass. It's almost not there. But it does still have that -1 charge. So it can still interact with different things in its environment, but it's not necessarily going to do that through its mass and through hitting something. It's going to do it through that electrical charge. They are often fast-moving particles because there is very little mass to them. And they do also come from decaying neutrons. Okay, so this is where things get a little weird. We're not going to go into all of the theory behind that because it gets really strange, and calculus and quarks and relativity and uncertainty principle and all of that stuff. So we're just going to stay at the surface with this one. But it is also related to what's known as a positron. Okay, so the positron is the same as a beta particle. It just has a +1 charge. So it's almost like a positive electron. Okay, so yeah, really strange there too. Okay. All right, gamma rays. So gamma rays are kind of one of the stranger ones. Their symbol is the Greek letter gamma, okay, which is, it looks like a Y, almost like a cursive Y. It doesn't have any mass, okay? It is pure energy, and it doesn't have a charge, okay? But gamma rays can actually cause quite a bit of damage just because of that energy that they have. So there's a video that I posted about the main 3 different types of radiation, and a guy is looking at them with a Geiger counter, okay? And at one point, he actually puts the gamma ray emitting material up to his head. Yeah, that's pretty much exactly what you don't want to do, because that was just not a good idea. But anyway, it does not have, it's not made of matter, and it does not have an electrical charge. So it is just pure energy, electromagnetic energy in the form of photons. So even with no electrical charge, simply because it is that much energy, it can easily ionize matter, just basically by pulling the electrons off just by pure energy. Okay? And at the atomic level, energy is kind of like muscle. Okay? The more energy you have, the more muscle you have. All right, moving on to neutron decay. So the symbol here is 1 over 0 N. So the 1 is referring to the single neutron. 0 refers to the fact that it does not have any protons. Okay, and then the N obviously stands for neutron. It has a mass similar in a way to the mass of an alpha particle, just about 1/4 of it. Okay, because it is just 1 neutron instead of 2 neutrons, 2 protons. It still does not have a charge. Okay, so matter that is released from an unstable nucleus, in this case a neutron, is referred to as neutron decay. Okay, so neutrons don't have a charge and they don't ionize matter, but they do have enough mass and speed when they fly out of these unstable nuclei, that they can basically break apart other atoms by hitting them hard enough. And we'll see in one of the next sections why that's such a significant concept. They will travel farther through materials than alpha or beta particles, simply because they're not really interacting as much. Okay, with alpha particles, you have both the mass and the +2 charge that's causing it to interact with things. With beta particles, you have that -1 charge. Okay, but here with neutrons, you don't have a charge, and you have about 1/4 of the mass of an alpha particle. So it can still travel pretty quickly and pretty far. So when we talk about how strong these types of radiation are, a lot of that, I mean, it's a good illustration to look at what can actually stop the different types of nuclear radiation. So if you have alpha radiation, those can actually be stopped by a piece of paper. Okay, so you don't need a whole lot to stop those alpha particles. Okay, beta particles can be stopped by aluminum or wood. Right, so if you have beta particles coming from the room next to you, all you have to do to prevent them from hitting you is shut your door. Okay? Gamma rays are a little bit trickier. You actually have to have a relatively thick block of lead in order to stop them. Okay? They have more energy than light or X-rays. Right? And you know, if you go to, say, the dentist, or if you go to get an X-ray done, they generally will give you that apron thing to put on. That is actually lead lined. Okay, because it is designed to stop the X-rays from going into your body where you don't need the image. Okay, so it protects you from getting extra X-ray radiation. Gamma rays have more energy than that, so you actually would need at least several layers of those lead aprons in order to stop the gamma rays. Okay, they do pose the greatest health risk, as they can easily pass through even thick fabric. So usually when you hear about people talking about radiation sickness or chemotherapy with radiation or anything like that, generally they're talking about gamma rays, simply because, I mean, they can cause the most damage and they're the hardest to stop. But that is the end of this section.